Section 2, the moon. This section is going to be one you probably want to focus on a bit. So we're going to go through the phases of the moon, what causes the phases of the moon, when the moon is visible. Alright, so we're going to look at first just the phases of the moon. Let's just name them. They're listed up here on the figure from A through H. It's a cycle, they repeat, so you could start it anywhere, but tradition is we just start at new moon. So here, this is what a new moon looks like. This is called a waxing crescent phase. First quarter, waxing gibbous, full moon, waning gibbous. Waning means that the lighted part is getting smaller. Third quarter, waning crescent, and then we would come back to new moon. So you probably want to take some time and learn them all in order, be able to sketch what each of them looks like, or at least be able to identify which ones they are. I always like to remember that the light starts on the right. So at the beginning of the cycle, the light starts on the right side of the moon, and the lighted part region grows and grows until full moon. And then it shrinks, it wanes, all the way back to new moon. So those are the names of the phases and the order that they're in and what they look like. What you should be careful about though is that this is how they look from Earth. This is only how they look from Earth. If you were somewhere else in the solar system, you would not see these phases in this order. So let me show you if you were above the Earth and the Moon system, like way high above the North Pole. So here in this figure we have sunlight shining from the left. So picture the sun far, far, far on the left. Sunlight shining on the Earth and the Moon. The Earth is this center one. Notice how half of it is day towards the sun. This half is day. This half is night. It's shaded darker. It's away from the sunlight. The Earth goes around the moon counterclockwise if you're above the North Pole. So let's start here at new moon, and it goes counterclockwise around the Earth. So at day 1, it could start here at new moon. About a week later, it would be here at first quarter. About a week later, it would be here at full moon. About a week later, third quarter. About a week later, come back to new moon. It takes about 4 weeks for one whole cycle. 29.53 days to be precise, but call it 4 weeks. If you're above the moon and the Earth, notice how the moon is always half lit up. The half towards the sun is lit up. The half away from the sun is in shadow. So once you see it that way, think about it, it should make sense, even though maybe you're not used to thinking about it in this layout. Okay. So let's look here. Let's start at 1 new moon. Right? From Earth, let's look at new moon. From Earth, we're going to look at new moon. And what are we going to see? We are going to see this dark side. We're going to see the dark side of the moon. Cue Pink Floyd. Right? We're going to see the dark side of the moon. And so it's really going to be not very visible. There's not going to be much light reflecting off of it. So that's new moon. We're seeing the half of the moon towards Earth. It happens to be dark. Now, kind of pay attention to where the Earth and the moon are compared to the sun. The moon is in the direction of the sun. The new moon is in the direction of the sun. So that means you would see it during the daytime. The new moon is up in the sky during the day. You don't notice it because it's not very bright, it's not very visible. You're looking at the dark side of the moon. Plus, the sky is amazingly bright. That's really the big reason. The sky is too bright and the moon is too dim, so you just don't notice it. It's there. If it's new moon and it's daytime, the moon is above your horizon. So you could imagine if you lived here, right where my cursor is, you would be at noon on Earth. Things in the solar system tend to rotate and orbit counterclockwise, so let's go later in the day. Later in the day means you're going to rotate over here on Earth. So this might be afternoon. Afternoon. So in the afternoon, a phase that you might see would be waxing crescent. Waxing crescent. And from the Earth's point of view, you're going to see half of the moon. So there's the half of the moon that you can see, the close half. And notice how most of that is dark towards Earth, but there's a little bit of light over here. And we would view that on Earth as a crescent. Just a little bit there on the right side of the moon is lit up. If you're thinking that maybe I'm wrong and that should be the left side of the moon, tilt your head or tilt your monitor so that way you're looking from Earth to the moon, and tilt your laptop so you're looking from Earth to the moon, and you'll see that it is the right side that's lit up. So waxing crescent is visible in the afternoon or evening. First quarter, when that would be above your horizon, is if you were somewhere on the evening side of Earth. And from the evening side of Earth, you would look out to the moon and you would see half the moon lit up and half the moon in shadow. You're looking at the near side of the Earth, or excuse me, the near side of the moon. So you'd see first quarter. The right side of the moon is lit up, the left side of the moon is dark. Right? It's because if you turn your computer monitor, your laptop, so you're looking from the Earth to the moon, the right side is lit up and the left side is dark. So each of these phases of the moon have kind of a characteristic time of day that they're up. So if I see a waxing crescent first quarter early in the cycle, I'm like, it's got to be evening time. Now let's flip it around. Let's look over here at the third quarter and the waning crescent. Same thing, same rules. You're looking from the Earth, you'll see half lit up, half shadow. Looking from the Earth, you'll see mostly shadow. A little bit of light for the crescent. But in order to see these phases, you have to be on this side of the Earth, which is the morning side. Noon, evening, midnight, morning. So the waning crescent, the third quarter, here, waning crescent and third quarter, they are morning phases. So pay attention to that in your everyday life. You wake up, you take the kids to school. I take my kids to school. Too early, I look at the moon, it's lit up on the left side. I'm enjoying my evening after the kids are in bed. I go outside and look, I might see a first quarter. The light is on the right side. It's an evening phase. The full moon and the gibbuses, waxing gibbous, full moon, waning gibbous, are visible mostly when you are on the night side of the Earth. Right? So go to your book, go to page 40, and what's helpful about this figure on page 40 is that it gives you the characteristic times when each phase is up. When it rises, when it transits, and what transit means is it's highest in the sky, towards the southern sky, and when it sets. And that depends on the phase. Your textbook covers synchronous rotation next, so let me see if I can flip over to synchronous rotation just to cover it a little bit closer in order to your book. Okay. So let's start off with the correct way. What's playing right now in this animation is the correct way. Have you ever noticed that when you look at the moon, you always see the same pattern of dark and light regions? You're always seeing the same side of the moon. The man in the moon. So from Earth, you look up at the moon depending where it is in its orbit, what phase it's in, right, what time of day it might be up, and you'll always see the same craters. You don't know, without looking at satellite photos or photos from the Apollo missions, what the backside of the moon looks like. You have no idea. The backside of the moon looks like this right here. Sorry for flipping on, slides on you. We'll go back to the animation here in a second, but that's the backside of the moon. You've never seen it unless you looked at a photo. Okay. And that's because the moon is in synchronous rotation. Synchronous rotation basically means that it keeps the same side always facing the Earth. That's it. It keeps the same side facing the Earth. That happens because the moon is lopsided. It has a heavy side. So here you've got the astronaut standing on the moon. He happens to be standing on the heavy side. Earth's gravity keeps the heavy side towards the heavy side of the moon towards the Earth. Earth's gravity has a hold of it. And the moon rotates. Can you see how the astronaut right here has his head pointing up on the screen? But now he's pointing differently. So the moon does rotate, but it rotates perfectly. One rotation, one spin, for one orbit. This is what it would look like if the moon didn't rotate. So this is incorrect. The way the animation is going right now is not true. But if the moon didn't rotate, you would be able to see both sides of the moon. The side you're familiar with and the side I just showed you, fully cratered, the side you're not familiar with. You would be able to see both sides. Here in the incorrect version, can you see how the astronaut is always in daylight? There would be a hotter side of the moon and a colder side of the moon. Permanently. Okay. But let's go back to the correct way. The moon does rotate. The moon is in synchronous rotation. The astronaut, wherever he happens to stand on the moon, in this case he's standing on the near side of the moon, he will be in daylight, he will be in shadow. But he always looks up from his position, and he always sees the Earth right overhead. If you were to land, maybe, can I pause this? I can't. Land in a different position and stand in a different position on the moon, you would see the Earth always rising, and it would never rise. We could land somewhere else and see the Earth setting, and you would always just see the Earth that same way. Or you could land on the far side of the moon, way back here, and you would never see the Earth. You would never ever see it if you landed back there and you were standing on the moon. So I told you that that's because the moon is lopsided, so I'm going to go back one slide to show you this again. The far side of the moon. I call it the far side and the near side because there is a permanently far side that we do not see from Earth, and there's a permanently near side. So here's the far side. Here's the near side towards Earth. Okay. The core of the moon, the heavy part, is not centered. It got displaced a little bit, moved to the side due to Earth's gravity and some tidal friction, which we might talk about later. Okay. So the moon's lopsided, and that got it stuck in synchronous rotation. It made the time frames line up perfectly. One rotation per orbit. Pink Floyd has an album called The Dark Side of the Moon. There is a dark side of the moon, but no part of the moon is permanently dark. So I'll go back here. If you watch, the lighted part of the moon changes. Each part of the moon in this situation gets light. So there's no permanently dark side of the moon. So I'll call it the near side and the far side. Then you guys move into eclipses. So let's go back to eclipses. Eclipses are the next thing we're going to talk about with the moon. We're going to start off with solar eclipses. So solar eclipses happen when the sun, the moon, and the earth line up with the moon in the middle. So here we have the figure, right? The moon in the middle. This is definitely not to scale. The distances should be much, 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 much bigger compared to their sizes, and even the sizes are just completely wrong. Okay. If the sun is a tennis ball, Earth is the size of a grain of sand. But it's a figure, so let's use it. The yellow lines just kind of show the different way that sunlight will get blocked by the moon. If you are in this tiny little region, right here, this tiny little region on Earth, you would end up being in a complete shadow. The complete shadow is called the umbra. And so what those yellow lines are trying to show you is just that there's no way you can get sunlight to that part of the Earth. It is completely blocked. Okay. So umbra, think of that as total shadow. This bigger region is called a partial shadow. It means if you were in this region, you would be able to see part of the sun, but not all of it. So some of the sunlight is blocked. So think of that as a partial shadow, or penumbra. Okay. So, solar eclipse, the moon has to be in between. So this is always new moon. It has to happen right at new moon. Has to happen right at new moon. It doesn't have to happen at noon. It would happen at noon for the people probably right in here, right there. But if you were over here, it wouldn't be noon. It'd be 1 o'clock, 2 o'clock, 11 a.m. Right? So a solar eclipse doesn't have to happen at noon. It has to happen at new moon. Right? There's 3 different types of solar eclipses you can get, just depending on how everything lines up. You can get the annular solar eclipse, the total solar eclipse, and the partial solar eclipse. In my life, I've only ever seen the partial solar eclipses. I'm looking forward to the total solar eclipse that's supposed to be happening in the Midwest in 2017. So let's see here. An annular eclipse. An annular eclipse basically means that the moon is too far away from the Earth and that the umbra doesn't even touch the Earth. So there's nobody on the Earth who can actually be in totality, be in the complete shadow, because the complete shadow doesn't touch Earth. Okay? And that happens when the moon is at new moon and slightly further away from the Earth. Because the moon's orbit's not a perfect circle. Sometimes it'll be closer to the Earth, sometimes it'll be further from the Earth. A total solar eclipse is when the umbra actually touches the Earth's surface. So the total shadow touches the Earth's surface. And you have to be in that tiny little location right in there in order to see totality. In order to see the total solar eclipse, you have to be in that small, total, complete shadow. The partial solar eclipse would happen if you were just in the penumbra at any point. So let's see here. Let me switch colors. How about light blue? So if you're here on Earth in the partial shadow, you would see a partial solar eclipse. But you could also do that up here. Here, oh look, these people right there on Earth, they would see a partial solar eclipse. And up here for the annular solar eclipse, you can probably have partial eclipse in here as well. Here's time-lapse image of the sun being eclipsed by the moon. So it would start off just being a regular day, the sun would be out, and then over time the sun would slowly get piece taken out of it, and that piece taken out of it would grow and grow and grow until the sun is almost completely eclipsed. You just have a crescent left. And eventually, if you're lucky, if you're on that specific small part of the Earth, you would be able to see totality. That would be when the moon would block out the surface of the sun, and it just lets you see the corona of the sun. It's kind of the upper atmosphere of the sun, and that's what that glare is around it. The corona is usually so faint you can't even see it at all. You're blinded by the mass of the sun, the surface of the sun. So only during totality can humans really see the corona with their own eyes. When this is happening, and I've observed it when it's in partial eclipse like this, you don't notice it because you don't usually look at the sun. The day will slowly get a little bit dimmer, a little bit dimmer, a little bit dimmer, but it happens so slowly your eyes just adjust. You don't really notice that the day is getting darker. If you're lucky enough and it's going to be a total solar eclipse, it would start to get darker and darker and darker until you really notice it and it looks like nighttime. I've heard that when totality is happening, animals get confused, birds would start to nest. I am looking forward to seeing that sometime in my life. Here's an image from space showing the umbra, the complete shadow, traveling across the surface of the Earth. Now really that shadow doesn't really move. It's actually the Earth is turning underneath the shadow. It's the Earth turning. But we're humans. We like to always picture the Earth, our position on the Earth kind of at rest. So our perception of it is that the shadow moves across the Earth that way, but it's really the Earth turning underneath the shadow. So solar eclipses, new moon, the moon has to be in the middle. If we go to lunar eclipses, it's the opposite. The Earth has to be in the middle. The sun, the Earth, and the moon line up with the Earth in the middle. And the Earth's shadow is going to be bigger than the moon's shadow because the Earth is bigger. So the Earth's umbra, the Earth's complete shadow here, it's going to be right there. And the penumbra, the partial shadow, is quite a bit larger here. So this is the overall geometry, Earth in the middle. If you look at this, take a second and think, what phase is the moon in right there? Sun, Earth, moon. It happens during full moon. A lunar eclipse can only happen during full moon. Okay. Kind of like solar eclipses, you can have different types of lunar eclipses just depending on the specific geometry. So the total lunar eclipse means that the moon is going to be completely in the umbra. We'll come back to why it has that reddish tint there to it in a second. A partial lunar eclipse is when it's partially through the umbra. And a penumbral lunar eclipse is just when it's completely in this partial shadow. I've never bothered with those. They're not as impressive to me. I've seen the partial lunar eclipses and I've seen the total lunar eclipses, the top two. Now, lunar eclipses, take about 4 hours to happen. It's the shadow is larger and the moon is moving through the shadow, so you've got a little bit of extra time. These are longer events than the solar eclipse. And 4 hours is a bit much for me to stand out at night watching the moon eclipse. So, you go outside, you look at it, you see it's in partial eclipse. Go back in another hour, more of it is missing. Go back in another hour, you'll see the moon returning back. So, sometime in your life, observe a lunar eclipse, but it's not as awesome as a solar eclipse. So up on the top of the screen, I have time lapse of a total lunar eclipse. So it started out as a full moon, and it starts out as a full moon. Eventually you'll see the umbra sneaking across there, and the umbra moving further across the moon. Right. And then the umbra covers the entire moon. And so you might ask, why is this so bright if it's in the total complete shadow? It's not really that bright compared to these other phases, or these other time-lapse images. It's just that the camera's shutter adjusted. The exposure was a little bit longer, so it makes it look brighter than it should be compared to these other ones. And if it's in complete shadow, why is it red? Why is there any red light at all? And if Earth didn't have an atmosphere, it wouldn't have the red tint at all. It would be in complete shadow. It would be dark, much darker than this. But Earth does have an atmosphere, and that can tweak the light a little bit and end up shining some red light on the moon. Okay. So of the sunlight, let me see if I can pick a color that's more obvious. How about yellow? Sunlight comes in, coming straight from the left, coming from the sun. The Earth is going to block most of it. All of this sunlight the sun would block. But there's a little bit of sunlight that doesn't shine right at the ground, but it just hits the top of the atmosphere. Just hits the top of the atmosphere. And air acts like a lens. It can separate out the colors of light and do a rainbow, and it can also bend their paths a little bit. And red light will bend more than yellow light or blue light. So as the sunlight goes through the air here, the green light and the blue light would still travel mostly straight, and it misses the moon, so you don't see it. The yellow light changes its path a little bit, is bent down this way, but it's going to miss the moon. Okay? It's really just the red light that is bent enough to shine on the moon and make it look a little bit reddish. Here's a little animation. Let me play it and then I'll talk through it a little bit. So we're looking at the Earth and moon from above, and then we look at it from the side. The green plane is the ecliptic plane. So the sun and the Earth are on the ecliptic plane. The moon's orbit is close to the ecliptic plane, but it's not perfect. It's tilted by 5 degrees. So sometimes the moon is above the ecliptic plane, and sometimes it isn't. So let me pan this one more time and pause it right here. Okay. So right here you have new moon. The new moon is as close to the sun as it will get, but it's a little bit below the ecliptic plane, so the shadow would actually miss the Earth. So you end up having a regular new moon, but not an eclipse. And if you end up here, you get full moon. Right there's full moon. The moon is directly behind the Earth, but a little bit above the ecliptic plane. So the Earth's shadow misses the moon. The moon's a little bit too high. So you end up with a regular full moon, not an eclipse. There's one more thing I should point out to you here. It's the nodes right there. Let's do this. A node is right when the moon's path crosses the ecliptic plane. So in this case, the node is right here, and there's one back over here, right back here. It's right when the moon crosses the ecliptic plane. Right? One node, two nodes. So in this animation that I just showed you, there should be no eclipses happening because the shadows never overlap. How do we get eclipses then? Let's make it a little bit more complicated and look at this animation. This is much more realistic. Okay. Let's focus just on the top one here. We have the sun, we have the earth, we have the moon. The moon is going to orbit the earth on its orbit here, and at some points in its orbit, here on this wider part, it's going to be above the ecliptic plane, and then down here is going to be below the ecliptic plane. And here's a node right there, right when it crosses, and there's the node right when it would be on the ecliptic plane. So I'm going to press play and just watch it for a little bit and just kind of see how the moon's orbit precesses while the Earth is orbiting the sun. I'm going to start reading off new and full moons. Full moon, new moon, full moon, new moon, full moon, new moon, full moon, new moon. Right? The full moon is whenever it's back here. Full moon is back here away from the sun. New moon is here in between the two. Now to get an eclipse, you need a full moon to happen on the node. So this little yellow part needs to line up. Or for solar eclipse, you need the new moon to happen when the node is there as well. So I'm going to go through now, play it again, and just narrate the eclipses. Solar eclipse. Waiting for the nodes to come around. Lunar eclipse. Solar eclipse. Watching the animation is much better than reading this in a book. So if you want to play that part of the video several times and watch the lower panels and try to really get a grasp on it, I would highly recommend that. Okay. So a lunar eclipse and a solar eclipse can only happen when new moon or a full moon happens at the same time as when the moon is on a node. We already did that. We already did that. Let's close with this. Oops, let me get my marker out of the moon. Remember how we were talking about annular eclipses for the sun? Sometimes the moon is a little bit closer to the Earth. Sometimes the moon is a little bit further away from the Earth. The moon's orbit is not a perfect circle. And so if you were to time lapse the moon through an entire orbit, it would look like this. It gets bigger and smaller just as it gets closer and further from the Earth. And it wobbles a little bit just because the orbit is slightly elliptical. This is called lunation, but it's not in your book at all. I found this on the internet and I thought it was an awesome image, so I thought I'd share it with you. This section will take you a few times to go through in the book or the lectures. Take the time and get used to it.